All right, so I'd like to welcome everyone to the 970th monthly meeting of ATMoB. Our guest speaker will be Dr. Priyanka Chakraborty from the CFA, and she'll be talking to us about what we can learn about the universe in the X-ray spectra. Come on, computer. There we go. So unfortunately, I had a little cold, so I wasn't able to go to the ATMoB New Year's, but hopefully many of you were able to go up there and have a great time. In past years, it's always been involved. Thank Eileen for organizing that, and everyone helped set up and take down the decorations. Thank you all. And so this is the typical agenda. Looks like one of Glenn's.
Looks like one of Glenn's cartoons.
You think after the 17th or 18th attempt, he'd probably get it.
Now I know why Rich donated one of these to him.
If your telescope is that out of collimation, you deserve it. It should never be that bad.
I like to do actresses down at the mirror.
Oh, space isn't remote at all. It's only an hour's drive away if your car could go straight upwards. That was Fred Hoyle, the astronomer. And this is paraphrasing from a bad memory, but I seem to remember Carl Sagan. Carl Sagan was an advocate for deep space probes to go to the planets. He was not a big fan of the space shuttle. And even made some point, something effective, you know, it's a tin can that you could drive to in a couple of hours by car. So he wanted to get way out there in space. Okay, we'll go to the next slide.
So this is the observing schedule for the clubhouse over the next couple of months. We still have volunteers that come up, weather permitting, of course, on the weekends, Friday, Saturday night of the new moon and last quarter moon, to give members a chance to come out under reasonably dark skies to do some observing and some imaging. And so there's the schedule up and coming. It's in the newsletter. Thank you, Al, for putting that in the newsletter. It's also on the event calendar. And so that's it. There you have it. The next slide, I think, just jumps right into what's going on with the planets. But before I get into that, did anybody get out there Monday morning and watch the occultation of Antares? Did anybody do that? No? It was lovely. It was lovely. I found the moon first. I realized the telescope I had out there wasn't focused. That's bad. If you're trying to observe in the daytime, you want to pre-focus your telescope on something, not the sun. That's not a good target to do it with. But so I was able to scoot right up to Venus, focus the telescope, go back down to the moon with about 10 minutes left. And Antares was a very pretty, sort of a pale, whitish, almost pink color. And the air was pretty turbulent coming off that storm we had on Sunday. But I watched it and watched it and watched it. And I always coach myself when I'm watching occultations to don't blink, don't take your eye off the star, don't be distracted, watch it, watch it, watch it, gone. It's fabulous. Now, I didn't know where exactly to look for the reappearance, so I didn't even try. But there were other things to be done that day, like figure out why the washing machine was overflowing into the basement.
Unimportant stuff.
Unimportant stuff.
That's right.
Anyway, but that's a different story. They're coming tomorrow again to try to fix it. Anyway, Saturn is setting during early evening. If you want to still see Saturn with its 8-degree ring tilt, you got to get out there pretty early. Southwest, right after sunset, the earlier the better. Jupiter is a Neptune and will set by 9 o'clock. Still almost 8th magnitude in Pisces. Uranus transits about 6:30, magnitude 5.6 in Aries. Jupiter is still the star of the show, shining at -2.4, currently transiting the meridian about 5:45 in the evening. Try to observe an hour before sunset. A couple of weeks ago, just for kicks, I decided to roll up in the observatory and look at Jupiter at 3:30 in the afternoon. Sun was still up. You know I like to observe in the daytime. If you have an alt-azimuth telescope and you play with the altitude and the azimuth, use your phone's compass, use your phone's tilt meter. You can find Jupiter in your finder scope while the sun is still up. And I could see Jupiter. The air was remarkably steady. I swear the air was really, really steady. Or as steady as it's going to probably be all night, in that hour right before sunset, maybe a little time afterwards. So I got a nice steady view of Jupiter. I could actually see the 4 Galilean satellites. I was using a 12-inch scope. No filters, but I could see the 4 Galilean satellites in the bright sky. The sun, like I said, I could see the sunlight still hitting the roofs of the neighbors' houses. So that was kind of fun. You should try that. Venus, of course, if you want to practice daytime stuff, it's still at magnitude -4. It's low, right? It's low in the sky now, but that's not so bad. 14 arc seconds, 80% illuminated. It's still 36 degrees from the sun. Mercury reaches greatest elongation west, 24 degrees away from the sun. That sounds really great, right? But the ecliptic, now we're getting towards springtime, right? And the worst case scenario is the ecliptic in the morning sky in the northern hemisphere in March, very shallow to the horizon. So even though Mercury is going to be 24 degrees away from the sun, it's very low above the southeast horizon, even at sunrise. So that's a tough observation. And even tougher probably is the daytime conjunction of Mars and Mercury on, I'm going to put it down there.
Yeah.
Well, sometime in January, I think it's the 27th. I think it's the 27th. They'll be 0.3 degrees apart in the early morning skies. I don't know if you'll be able to see them. Mars is like plus 1.2 magnitude. That's pretty faint for daytime. Mercury's brighter, so if you could find this guy, maybe you might see him in the telescope. But those are some of the planetary things that are going on. There are some other things to look at in the sky if you are so inclined. Asteroid Vesta is making a pass, and thanks Sky and Telescope for this fine chart. It's a little outdated, but Vesta is asteroid number 4. It's a little bit under 300 miles across, currently subtending about a 0.4 arc second disk. And right now, it's near Zeta Tauri. That's the one of the tips. That's the tip of one of the horns of the bull, and it's moving up towards Omicron, right where it says plus 22 over the next 10 days or so. So it's right in that part of the sky. It's about magnitude 6.7, 6.8, 6.9. I think it's even brighter than that. I can't remember. Too many numbers swirling in my head. I could see it in binoculars last night. So if you are interested in looking at an asteroid crossing through Taurus, this is a good opportunity to do that. And there's one other thing that we should be aware of is Comet 12, the period of Comet number 12, Pons-Brooks. Now, this may sound pessimistic. It's at 11.8 magnitude in Cygnus. But this comet is very prone to outbursts. And it's been undergoing outbursts now for the last probably 9 months. And every now and then you'll see it hit the news, the astronomical news, that it's in outbursts. By April, it's expected to be about plus 4.5 in the evening sky, so that could be a pretty nice comet to look at. The reason you want to get it in now is because this light curve shows the brightness variations over time. This is 2024. This is 2090. Okay, so I'm going to probably have to skip that one. Yeah. It orbits the sun about every 70 years. So if you wanted to take a look at this comet, this would be the year to do it. That's it for special stuff. What's next? What's the next slide? Oh, it's the double star of the month. You know, last month was Kid, right? Right here in Eridanus. Here are the stars of Eridanus. And there's Rigel right there. And so last month's star was Kid. It's right here. I hope you checked it out because it's a really nice multiple star. But 32 Eridani is a little off the beaten path. I bet it's one of Glenn's favorites.
Oh yeah, it's beauty.
Struva 470. It's a beautiful yellow and white pair of stars. Unequal in brightness, close, 4.7, 5.9, 6.9 arc seconds. Very pretty. Very well worth the hunt for that one. So that's, I hope you'll get out and take a look at that. Very well placed in our January skies. And what's next? I can't remember. Oh, now it's on the Observer's Challenge. Well, you do this part. You do this part.
First, I want to go back to that cartoon. I just happened to, when I want to find cartoons to put on the Observing Committee report, I just Googled astronomy cartoons, and that one came up. And so I did a little research on that one. Actually, that came from a thread in Cloudy Nights. And there was a guy that put out that he likes to do astronomy cartoons, and he couldn't find a place to publish them anymore. So he put it in Cloudy Nights, and everybody jumped at it. There's a whole thread. It even went to, I think there was one earlier last year. So I'm going to start putting those out. The guy is a good artist. I mean, this looks almost like The Far Side. And so I'm going to put a couple of those out and for future events. Okay, now we'll go to the Observer's Challenge.
You should never really stare into the laser light, you know that.
You know, though, I showed you that cartoon, then you lent me one of those laser collimators.
Sure, you needed one.
Anyway.
Like I said earlier, if your telescope is that out of collimation, then, man, that's crazy. That light shouldn't come out of the tube at you like that to scar up your face.
Yeah,
Anyway.
do not stare at the beam with remaining eye.
That's right. Do not stare at the laser.
First of all, a little egg on my face. I talked about I see objects being I can't see objects. And IC10, which was the November challenge, I gave it a couple of tries with a 10-inch no luck at all. So I didn't even bother. What was the one? It was IC1848, the Sol Nebula. I didn't even try it. And then I happened to look at Sue French's book, and she had mentioned seeing it with a small aperture telescope. And the more I heard, in fact, the report now, Roger Iverson comes out with the report, observing challenge report. And there are about half a dozen ATMoB members who put in and forwarded things in, and I thank them again. But one, I gotta remember, there was John Bishop, a club member, and I guess he observed it from the clubhouse a couple of times with binoculars, with image stable binoculars. So what I'm going to do, again, and the other thing is, I would have looked at it now with my astro scan, but the clouds have been there. You know, skies have been pretty cloudy, and I want to get ahead and look at the object for this month and then for the next month as well. So I'm kind of behind, but if you want to check that one, I'd say try a small aperture wide field telescope. Now this one is NGC 936, and this one is easier again. We go back to something you can see with a backyard telescope. And it's located not too far, it's near the head of Cetus, not too far from Omicron Ceti, Myra. And right near a star called 75 Ceti, this is about a 5th magnitude star. I star hop there by, these are the 3 main stars, Alpha, Gamma, and Delta. And then there were 2 stars right in this finder scope view, and I just picked the lower one, and then it was a quick star hop about 1 degree, and it got me to that galaxy. We'll go to the next slide. We got some images for people in the club. It's called the Darth Vader's TIE Fighter, or the Darth Vader Galaxy. You can see why. I mean, this is an amazing object. It's a lenticular galaxy, and this is Doug Paul's picture. So, Doug, if you can give us the particulars on this shot.
Well, the center is pretty bright. The bars are medium, and then the ring gets really dim. That's about 7 hours with a 6-inch aperture.
All right. While that one is up there, William Herschel discovered this, I think it was in 1785. And what he saw apparently was this part right here. There's a bright central part with the haze around it. So he thought it was a planetary nebula. He categorized one of his class 4 objects as a planetary nebula. I don't believe he saw these outer parts at all. Now we're going to move a little bit closer. The next one is Mario Matas. I don't see him physically here, but if he's online, Mario?
Yes, hi. Hello, can you hear me?
Yours.
Yeah, this, I actually took it twice because 936, as you can see here, I realized after I took it when it was centered that I just missed 941 off to the side, which is a spiral. And I like to get multiple galaxies and images, so I retook it, and this is the result. I'm not sure why it's called a lenticular, though. It's got a bar in the center. So,
Yeah, I think it was a barred lenticular galaxy.
yeah, it's probably a closed spiral. I don't know. I'm not sure it should be called a lenticular. I tried to look at things up on it, and they do call it that. I'm wondering why. Anyways, this was red, green, blue, about 2.5 to 3 hours of imaging.
Nice shot of a double star, by the way. Very good.
This galaxy here looks almost flocculent. You can see it's got some spiral arms, but it looks almost like a flocculent galaxy.
12th magnitude, so that might be a challenge for backyard telescopes. Now we're going to move in a little farther away. Each of these is moving farther in a wider field. So the next one, I believe, is Chris Elliger's. Nice shot. Go ahead, Chris.
Yes, this is from the Middleman. So this is the full frame that we get with the telescope. So you get there's a lot of galaxies scattered throughout. The 2 prominent ones, I don't remember it's a UGC down below on the left, I think. I don't remember the number though. But there's lots of other smaller ones all scattered throughout. So yeah, this was, I believe, 2 hours of luminance and then half an hour of each of the photometric color filters.
Okay, I want to point out a little asterism up here. Those 4 stars fairly bright, and a couple more right in this area, right in here. And I'm doing that because the next slide is of the sketch I made, and we'll go to the next slide. Now, this was 30 minutes of eyeball observing and 30 minutes of freezing my ass off. But if you looked again, there's that asterism up at the top, and then Chris's picture and the other ones, oh, you see the size right there compared to these stars right here. Now go back to mine. All I got was that nucleus part. I saw what William Herschel saw, so it did look a lot like a planetary nebula. And this was with a 10-inch reflecting telescope. What I did the same night was I took out the 4-inch. I gave that talk last meeting about small telescope astronomy. I had a little 4.5-inch scope, that Orion scope that I use now and then. You could see it with that with averted vision. I have no doubt in my mind that out in the country you could see it with no trouble at all. In fact, my 3-inch that I talk so much about, I'd be able to pick it up with that telescope because there are Messier galaxies that are fainter than this. The problem is with light pollution. When I did all that Messier catalog with that 3-inch scope, I had magnitude 6 skies. I don't anymore. And then we'll go to the next one. Our object for next month is NGC 1579. It's called the Northern Trifid, and it's not too far from, I think that's Psi Perseus. It's about a 6-degree star hop. I did try for that with a 10-inch the other night. I just gave it a shot because the weather's been terrible. And when I went out, it was a couple of nights before the storm we just had, and the skies, I went out and it just didn't look right. And when I looked at the little dipper, I could see maybe down to 4th magnitude. I couldn't see those 5th magnitude skies there. So I was working with 4th magnitude skies, and with a 10-inch I couldn't see anything, even with a filter. So I'm gonna have to wait till we get a really nice clear night to look for this one. It's about, I think 15 degrees apart, or 15 arc minutes apart by about 8 arc minutes. I don't have a magnitude because a lot of times with nebulas they don't publish them, so I'm not sure what the magnitude in that one is. But again, I did not see it with a 10-inch scope and magnitude 4 skies, so you're going to need clear skies for that particular one.
It's not on this chart, but while you're in that area, there's a really nice planetary that's located right about in here. It's on NGC 1514. It's really pretty. It's got a 9th magnitude central star. And if you wonder how could a planetary that seems to be so far away has a 9th magnitude central star, is that the 9th magnitude star is not the progenitor of the nebula. It's actually a binary system. And the progenitor is invisible, and the companion, the 9th magnitude companion, is what you see in your backyard telescopes. 1514 enjoys a filter, and you'll enjoy it also. I would recommend a UHC or Oxy 3 if you've got the aperture to drive the light through it. But that's a bonus object in that field of view. It's a nice planetary. You should check it out.
Okay, I think that might, unless you had other slides.
Well, I just kind of got the summary of those objects. 936 Kepler and Saturn, those are those big fat books they sold us. Magnitude 10.2 with a surface brightness of 13.5. NGC 1579, 3 stars, reflection nebula. So I don't know how well it would deal with filters, right? Reflection nebula, it's not an emission nebula. So
It does have a good bit of hydrogen in it.
does it really? Okay, well then maybe you can get away with the UHC, right?
I will throw out, and I looked at the book by Kepler and Sander, and they go by telescope size. They'll do 6-inch, 10-inch, and so forth. And the smallest one they started with was like 12 to 14-inch telescopes. That doesn't mean you can't see them with smaller scopes, but it gives you an idea. This will be a bit of a challenge.
Look at the size. It's relatively large, right? The moon's 30 arc minutes in diameter most of the time.
I've half the moon.
Mario, you knew about that, right? The moon's 30 arc minutes. But, sorry. But here's a real treat coming up in March. The March objects, NGC 2440. It's a beautiful planetary in Papas. Kind of a little bit far south, but that's really worth the hunt. It's a beauty. I know it's a fine object and should be on your observing list. So looking ahead a little bit, you should check that one out. That's a pretty fun one. And if you're unsure of where any of these things are, they're almost always plotted in the Pocket Sky Atlas by Sky and Telescope, or Deeper Star Atlases will show them as well. Come on, if you're really struggling to find any of this stuff, come on up to the clubhouse when we're observing, and we'll find it. We'll show it to you through the telescopes. And Steve, go ahead.
You and I saw a 936 incidentally at the clubhouse.
We did.
wasn't too bad. Wasn't too bad.
We used your 18 and we used the 25. It was a fairly bright object. Now, we've got aperture behind us, but it can be done.
Could you see the fins of the TIE fighter, or did you just see the nucleus in that?
Mostly the nucleus primarily. Yeah, it wasn't tiny, but it was bright, but nothing in the.
And that was with the 25?
The 18 and.
18. Okay.
Sometimes when we're working with a 25-inch scope at the clubhouse, we're moving through objects fairly quickly. And for a faint halo like that galaxy, it would be wise to dedicate some time to observing it, no matter what aperture you're using. Jack up the magnification as high as the sky will allow, it'll darken the background, and then spend some time looking at the galaxy and let the photons just kind of charge up your eye and see what you can actually see. It's a quote that sometimes is attributed to Michael Covington, but he claims it's not. But somebody once said, for faint galaxies, you should give each one at least 15 minutes if you're going to visually observe it. Don't let the light, let your eye, it's happened to me so many times. You look at an empty patch of sky that's got stars in it, the eyepiece, there's nothing there. And about 3 minutes later, wait, and then 5 minutes later, you can see it. And then a half an hour later, it's like, how did I even miss that thing a half an hour ago?
And then your neighbor turns his backyard light on.
That's right. And I will say, now that we're in winter, I know we've been blessed so far with torrential rains, but once that snow hits the ground, the light pollution goes off the charts, right? Because not only is it shining up, but it's reflecting off the snow. And so my backyard runs about 4.3, and now move about 4.38 with the snow on the ground.
One other point with observing galaxies especially, and reflection nebula, wait till we're on the meridian or near the meridian. There's an enormous difference in these low surface brightness objects. When they're low near the horizon, anything below 20 degrees is almost hopeless. You'd be amazed when they're higher up, particularly the ones that are above maybe 40 degrees.
Sure.
Up, 40 degrees up.
Even on the
quite visible.
Even on the clearest of nights, the atmospheric extinction, you'll lose about 3 magnitudes as you get near the horizon.
Right.
3 magnitudes. And I imagine that's point sources, high surface bright objects. These faint little galaxies just disappear into the murk.
That's right.
So
planetary nebulae can compensate for an emission nebula with a filter. Galaxies are hopeless. You just can't.
It's tough.
It's a low surface brightness. You really have to pick the right moment.
Absolutely.
The right conditions.
Yep. And again, come up to the club, let's pick our brains. Steve and I are more than happy to chat with people. Come observe with us. You'll have a blast. You look at all kinds of things. Even the moon sometimes. Sometimes that's 25 inch on the moon. You should see it in that telescope. Oh my gosh,
You can feel it in that telescope.
Unbelievable. You know the guy with the laser? That's what the moon does to you when you put the 25 inch scope with no aperture mask. Go full aperture. If you're going to do it, just do it. It takes about 3 hours for your night vision to come back. That's just in your observing eye. So I think that's it for the observer's report. Okay. I know the next slide is the outreach report. So I'm going to stay up here with me. Stay up here, part of the outreach committee. Stay here with me.
All right, I will just say this, as always, keep looking up.
Oh, absolutely.
Unless it's raining. And I don't know if there's anybody here who knows, is this a rural myth? I heard that turkeys are so stupid that if it's raining, they look up with their beaks open and they drown. Is that anybody here that knows?
Maybe domestic ones, certainly not wild.
Okay. All right, your show.
right,
Thank you again.
We'll introduce the speaker, Dr. Priyanka Chakraborty. She'll be talking about what we can learn about the universe through X-ray spectra. In this presentation, we'll embark on a journey through the evolution of X-ray astronomy, spanning several decades, detailing how X-ray spectral lines have provided invaluable insights, unraveling the secrets behind the most energetic processes in our cosmos. Dr. Priyanka Chakraborty has been a postdoc researcher here at the CFA for 2 years. She specializes in high-resolution X-ray spectroscopy, utilizing data from telescopes such as Chandra and XMM-Newton. She's a key developer of the AtomDB spectral synthesis software and a member of the newly launched XRISM team, a collaborative mission between NASA and JAXA. So please welcome our guest speaker. be able to present whenever you're ready.
So I need to connect.
Should be able to just present through Zoom. So when you present to Zoom, it'll come back onto the screen. This is USB-C. What's this? Seems to be working.
Can you turn the lights down a little?
Sure.
So we can see all those X-rays.
Hi everyone. Thank you for being here today. So in this talk, I'm going to be talking about what can the universe teach us through X-ray astronomy. So X-ray emitting objects are so important because they represent the hot and energetic part of our universe. So these are the
That's part of the.
They did revamp this room, so this is a slightly newer system. Let's see. Testing 1, 2? Yeah. Yay.
Thank you.
I should be able to click in.
So these are the systems that are like several thousand times hotter than the surface of our own sun. And so they represent the hot and energetic parts of our universe. And because if we want to understand the large-scale structure formation or the evolution of our universe, it is very important to study these X-ray emitting targets. Okay, so you are probably very familiar with X-ray in doctor's office. This is an example how your hand might look like under the optical light and the X-ray, and as you can clearly see, they are obviously very different from each other. Similarly, this is an optical image of our night sky. This is something similar to what you can see if you look up or look through the sky with an optical telescope. And this is an X-ray image of the same section of the sky. As you can see, it looks very different. These central portion, it's actually representing this galaxy cluster, and then you can see that the center is really bright, and if you go towards the outside, the X-ray becomes fainter and fainter. So this is an image of a galaxy cluster, which is related to the large-scale structure formation. And so we can study systems like galaxy clusters to understand the large-scale structure formation and evolution of our universe. Okay, so now that we understand that why it is important to study these X-ray emitting objects, the next question that comes to our mind is how do we detect these X-rays? So this figure here is showing the atmospheric opacity with wavelength. So the X-ray is like around here, and as you can see, for X-ray emitting objects, the atmospheric opacity is 100%. That means none of the X-ray is going to penetrate the Earth's outer atmosphere. So it is not possible for us to detect these X-rays using ground-based telescopes. In contrast, as you can see with visible light or optical light, the opacity is very close to zero, which means most of the visible light is going to penetrate through the Earth's atmosphere. And we are going to see the visible lights with ground-based observatories. So because the X-rays cannot get through the Earth's atmosphere, it's actually good for the life formation in Earth because if those strong X-ray radiation was getting through the atmosphere, that can cause very serious cell mutation in all the living objects, and it's going to be very bad for the existence of life if the atmospheric opacity was not 100% for X-rays. But this also means that for us astronomers, we have to make extra effort to make these satellites and observatories and launch them into space so that we can make these observations. Okay. Can you hear me?
Just turn it on a little bit. Does that work?
Can you hear me in the back?
Yeah. Is the microphone working back there?
Say something.
Hello?
Hello.
That's right.
Okay. So these are some of the objects that emit strongly in X-ray. You're obviously very familiar with stars. Some of the stars, some fraction of them emit X-ray. The stars that are really, really hot, that can emit in X-rays. And then there are objects like X-ray binaries, which is this combination of two stars. And then one of the stars is accreting material from another companion star. So they can also be very strong source of X-ray radiation. And sometimes we see that there are these strong high velocity stream of gas that shoots out of the object that gets accreted, that accretes the matter from the companion star. So that's something we call jets. And if the jets are emitting in X-rays, we call them X-ray jets. There can also be supernova remnants. These are the astrophysical objects. If a star comes to the end of its lifetime, it can blast into this. It can blast out its shell, so that the shell becomes a very strong X-ray emitter. Similarly, galaxies can also be strong X-ray emitters. These are the objects that hold many stars, stellar remnants, dark matter, interstellar medium together, hold together by gravity, and they can be they can emit X-ray radiation. And then galaxy clusters, which if 100 or even 1,000 galaxies can come together, and they can be gravitationally bound to make these huge structures called galaxy clusters. And they are actually the largest gravitationally bound structure. So if we want to understand the large-scale structures in our universe, so we need to study galaxy clusters in detail. In the next few slides, I will go into details of dynamics of galaxy clusters and why it's important to study them. So here are some of the techniques that we X-ray astronomers use to understand about the mechanism of these X-ray emitting objects. The first one is imaging. It's pretty obvious. You just take a picture of the object, like you take a picture of an object with an optical telescope. It's pretty similar if you take the picture of an object with an X-ray telescope. And as you can see, this is actually taken by a telescope called Chandra, which I'm going to be talking about Chandra in a little bit, but it can see structures really well. And as you can see, the center is hot and then the outside gets cooler. And by looking at these structures, you are able to tell about the dynamics or the gas properties inside the system. So it's a pretty effective way of learning about X-ray emitting objects. Similarly, another useful technique is spectroscopy. It's something similar like optical spectra, but the techniques are a little bit different. I'm also going to show you how X-ray spectroscopy largely works. So you want to be able to look at these individual lines, and we can understand about the temperature, the turbulent velocity, which gives us an estimate of how much disturbance there is within the system. We can understand about their metal content, etc. So both of these are very useful techniques that we use to interpret X-ray data. So the very first X-ray detection was actually made in the late 1940s, and we know that sun emits in X-ray since 1948. There were these cassettes with photographic plates that were flown outside the atmosphere, which detected X-ray radiation from the sun. These are World War II rockets, and they had these photographic plates behind aluminum and beryllium windows. So they did the test like this. So they checked if there is any blackening in the photographic plates because they were behind aluminum and beryllium windows. Typically, you would not expect the visible light to get through those windows. But when they got the plates back, they saw some dark spots there. So that's how they confirmed that the sun is a very strong X-ray emitter. But at that point, scientists did not know that if there are other extrasolar objects that also emit in X-rays. So the next X-ray mission that was launched was the ATMoB rocket, which made the first ever detection of an extrasolar source that emits in X-ray. It was launched on 1962 by Riccardo Giacconi and his team. They actually launched this rocket to study X-ray emission from moon, but they detected some unexpectedly bright X-ray signal that cannot be coming from the moon. So they came to the conclusion that there must be some other extrasolar source that is emitting such strong and intense X-ray radiation. So the name of the source is Scorpius-1. It's an X-ray binary, and this is actually showing the artist illustration of this object, and it became the very first X-ray source discovered outside the solar system. And this was actually a very pioneering work by Riccardo Giacconi, because this is what paved the path of modern astrophysics, modern X-ray astrophysics. And this was the first confirmation that there are X-ray radiation that can come outside our sun. So because of this incredible contribution, Riccardo Giacconi received a Nobel Prize on 2002 in physics. So now that we know that, scientists knew that there are other extrasolar X-ray emitting objects, they launched a NASA satellite mission for exploring the X-ray sky. It was called Uhuru, and it produced the very first comprehensive catalog for X-ray emitting objects. It included 339 objects. If you fast forward to today, now we know millions of X-ray sources, and it's actually a really giant leap if you think about it. But this is where it started from. So this is an image of the Uhuru satellite in the making, and there was a proportional counter detector in the satellite. So the way these detectors worked was the X-ray were heating up this gas chamber that had these gas atoms and molecules, and the X-ray will interact with the particles to produce these electrons. And there are some cathodes and anodes there, so the electrons will rush to the electrodes and make an electric signal. So the X-ray was being converted to that signal, and that was being detected. As you can see, this was actually a huge improvement over the previous photographic plates. The next X-ray observatory was called Einstein. It was launched in 1978. It was actually 100 times more sensitive than Uhuru and 1,000,000 times more sensitive than the ATMoB rocket. Einstein ended up discovering approximately 5,000 X-ray emitting sources, and it got X-ray data from different supernova remnant galaxies, clusters of galaxies, and X-ray jets. So there were many other X-ray missions that were launched after Einstein, but one of the NASA's great observatory is the Chandra X-ray Observatory, which is sensitive to X-ray objects 100 times fainter than the previous X-ray observatories. Chandra has the best angular resolution, which means among all the telescopes that I'm going to talk about today. Which means Chandra can see the structures in an image really well. It was launched in 1999. It was actually a 5-year planned mission, but it's been successfully running for 24 plus years now, and it's also been making significant discoveries. So this was the grading spectrometer that was in Chandra. For the first time, they were using this kind of spectrometer that will produce really good quality spectral lines. The X-rays enter through these X-ray mirrors that sort of focuses these photons, and this is called an grating, which is basically parallel slits arranged parallelly. So when the light focused by these mirror enters these slits, they then when they are incident on this detector, they can produce these patterns that are called interference pattern, and then you can see these beautiful X-ray spectra. It's actually a little bit different from what you see in optical telescopes, where you just place a prism in front of the light and then you see a rainbow of light, a rainbow of lines, and that's how you can detect the optical spectra. But X-ray spectrometer meters more or less work like this. And this was again another huge improvement over the proportional counter that was being used in the previous Uhuru telescope. So you can see that how much the detectors have been evolving in the past 30-40 years, and now we can get really good spectra using X-ray telescopes. So I have a video here showing some of the great discoveries that Chandra has made. This was actually released on the 15th birth year of Chandra, and it nicely sums up the great discoveries that has been made in 15 years of its operation. So I'm going to play the video. I'll up the sound a little bit.
In 15 years of operation,
we have booster ignition and liftoff of Columbia, reaching new heights for women in X-ray astronomy.
The Chandra X-ray Observatory has given us a view of the universe that is largely hidden from telescopes sensitive only to visible light. Chandra has captured galaxy clusters, the largest gravitationally bound objects in the universe, in the process of forming, and provided the best evidence yet that the cosmos is dominated by a mysterious substance called dark matter. Chandra has observed gas circling near a black hole's immense horizon. The atoms of this gas are doomed to destruction by the extreme gravity of the black hole. Most of the elements necessary for life are forged inside stars and blasted into interstellar space by supernovas. Chandra has tracked these elements with unprecedented accuracy. Young stars are crackling with X-ray flares and other energetic radiation. By monitoring clusters of young stars, Chandra can give us a sense of what our young sun was like when life was evolving on Earth. Chandra, taking us on a unique voyage into the big, bad, and beautiful universe.
So those were the list of discoveries Chandra had made in the first 15 years. There have been many after that, but I couldn't find a video of all the discoveries for the past 25 years. But I think this pretty much sums up most of the major discoveries that Chandra had made. So the next few important extend missions were XMM-Newton and Suzaku. XMM-Newton was actually launched just a few months after Chandra in 1999 December, and then Suzaku was launched in mid-2005. The next three missions, Hitomi, XRISM, and Athena, these are called microcalorimeter missions, and they are actually very different from the previous missions in the sense they can see the spectral lines with unprecedented accuracy. So they are going to be able to tell us about the hot and energetic universe with an accuracy that never existed before. So Hitomi was a telescope that was launched on 2016, and unfortunately Hitomi, because of some technical difficulties, its lifespan was only 1 month. But in this 1 month of operation, Hitomi observed the spectra from Perseus galaxy clusters, which I'm going to be showing you in some of the next slides. And it was actually a very beautiful spectrum, which could not be observed with these previous telescopes, because it was a microcalorimeter mission which could detect these spectral features with unprecedented accuracy. I also have a slide next showing you how microcalorimeters works and how does the systems works in microcalorimeter missions. XRISM is actually a follow-up mission of Hitomi, which is going to recover most of the science objectives of Hitomi. It was launched a few months ago. There were a big press release. You might have, some of you may have seen the press release for XRISM. And then the mission Athena is going to be launched in 2035. So this is how the microcalorimeter detectors work. If you have this array of incident X-ray photons in this material called an absorber, then the X-ray photons gets absorbed in the absorber, and it releases some of the electrons from the absorber, and then the electrons sort of moves and rattles around and increases the temperature of the absorber a little bit, which is then detected through this thermometer. But the special thing about this system is this thermometer can detect really tiny changes in the temperature, in the even in the millikelvin order, so which is 1 divided by 1000 Kelvin, or 1 divided by 1000 Celsius even. So because it can detect these tiny changes in the temperature, it can make really precise measurement of these X-ray photons intensities or energies. So that produces this spectrum that we can see the features of the spectral lines really, really well if we are using the microcalorimeters. So Hitomi and XRISM has microcalorimeter in them, and Athena is going to have microcalorimeter detectors. So obviously I have talked about so many telescopes so far, but you might ask the questions, why do we need so many telescopes? And that is because we want to have 3 qualities in telescopes. One of them being the effective area, which means the larger the collecting area of a telescope, the more photons you can capture, and there will be more signal to your telescope. And that's good because you can see the objects more clearly. The second quality is the spectral resolution, which means which decides how well you can see the different lines when you look at a spectrum. And the third quality is spatial resolution, which determines how well you can observe structures. So, for example, sorry, this is really slow. Okay, so for example, this is the image of the supernova remnant Cassiopeia A, and this image is taken by the Chandra telescope, this image is taken by the XMM-Newton telescope, and this image is taken by the Suzaku telescope. So if you look at this image, you can clearly see these different structures, different colors, you can distinguish them. So you will be able to learn about the properties of the system with precision. But and this is because Chandra has really good angular resolution. But if you look at this image here, you can still kind of see the structures, but it's a little bit blurred out. And that is because XMM-Newton has worse angular resolution than Chandra. And then if you look at this image, this was taken by Suzaku, you cannot see the structures at all. And it's because Suzaku's angular resolution is worse than both Chandra and XMM-Newton. So similarly, in terms of spectra, I have shown the comparison between 2 spectra. The black spectrum is the spectrum of Perseus taken by Hitomi, which has microcalorimeters and is able to detect those precise changes in a spectrum. And that's why you see these lines very, very well. Like you can see 4 different lines here, 2 lines here, 2 here, and many different lines here. But the red line here is the spectra of the same object observed by XMM-Newton. And because the spectral resolution of XMM-Newton is not so well here, like at this energy range, that's why you cannot see any structure here. So this is why you need telescopes with good spectral resolution. Now, you might ask the question, why can't we make a telescope that has all 3 qualities, like we have good effective area, good spatial resolution, and spectral resolution? They can be really, really expensive to assimilate all these properties in one telescope. So that's why we have different, and each of them serve a different purpose. So like I had mentioned that the recently launched X-ray mission was a XRISM, and it is actually going to answer a lot of the big science goals that we have in astronomy. So the first one being how were the galaxy clusters formed? So galaxy clusters are these large-scale structures. Their largest gravitationally bound structure And this simulation is showing you how large-scale structure has formed and evolved over time. So you can see that these like web-like structures, those are the cosmic filaments. And then the little dots here, they are galaxies, and they are coming together here, being gravitationally bound to form these clusters of galaxies. So that's why if we want to understand these large-scale structures, it is very important to study clusters of galaxies. But this is obviously a simulation, and we still have many unanswered questions of what actually happens out there. So that is why we need observatories like XRISM, which can actually make those observations and tell us what happens out there, is if it is exactly identical to this simulation or it's something else that we don't know about yet. Another important question that XRISM is going to answer is what is the hidden dark matter distribution in these large-scale structures. And so about 85% of the matter content is dark matter, and so you would expect that in a galaxy clusters, a significant fraction of the matter will be dark matter. We can assume 80-85%, but actually we cannot see these dark matter because they don't emit anything, they don't emit any radiation. So that is why actually the dark matter is gravitationally bound to the matter that is emitting in X-ray radiation, like this matter I have shown here. And because the dark matter traces out the visible matter, we call it, gravitationally traces out each other. So if you know the structure that is being made by this visible matter, you'll be able to say the dark matter also is tracing the same path. And we'll be actually be able to tell what is the hidden dark matter distribution in these galaxy clusters or in our large-scale universe. So this is an example of an XRISM observation of a galaxy cluster. It's just a snapshot of it. And these green boxes are regions at different radiuses from the center to the outside. And we could just take these sections and study the properties of the material within that section, and we can make plots like this. So this is the velocity, the change in velocity for different regions. So you can see the velocity is changing, which we can measure with different by studying different regions. Similarly, we can also trace out the temperature, like we can measure the temperature at these different regions, or even the metal content of these different regions, and that's the way we can tell how is the dynamics of the galaxy cluster, which is directly related to how these the formation and evolution of galaxy clusters as well. So this is another thing that XRISM is going to be able to do. It can trace out the chemical composition and evolution of our universe. So this is a spectra taken by XRISM for Vargo cluster. And as you can see, you see multiple lines here, some of iron lines, magnesium, sulfur, silicon, argon, calcium, many different lines here. And so we can see, because we can see these lines so clearly now, we'll be able to track the chemical enrichment history of the intercluster medium and our universe, and we will be able to put tighter constraints on the mechanism that produces these chemical elements. So I have a video of the launch of XRISM that was made a few months ago. It's actually a collaborative mission between NASA and Japan Aerospace Agency, and this was actually launched from Japan.
Flight mode on. The flight mode is on. The thermal battery has been activated.
全システム準備完了。
All systems are go.
Main engine start.
The main engine ignition.
Throttle PA 点火。Lift off.
Solid boosters ignited.
Lift off. プリズムスリムを搭載した H2A ロケット47号機は2023年9月7日午前8時42分11秒に種子島宇宙センターから打ち上げられました。
We have a liftoff of the H2A launch vehicle number 47 from JAXA Tanegashima Space Center at 8:42 and 11 seconds a.m. on September 7th Japan Standard Time.
打ち上げ以降、ロケットの管制は吉信発射管制塔から竹崎総合司令塔に引き継がれています。
Following the liftoff, the operation control of the H2A has been switched from Yoshinobu Blockhouse to Takesaki Range Control Center.
So the first light images and spectra from XRISM was recently released. This is actually the first light observation of a galaxy cluster called Able 2319, and this violet light you see here, that's the X-ray radiation that's permeating through those galaxies inside this galaxy cluster. Actually, XRISM observations of galaxy clusters like this will provide us insights into how universe produced and distributed different chemical elements. The hot gas within clusters is actually a remnant of birth and death of stars happening over billions and billions of years. So XRISM will actually be able to discover which metal it contains and map out how the universe was enriched with these metals. So this was another first light observation that was released recently of the supernova remnant N132b. This image here, this is the image taken by the imaging camera in the back. Different colors means different temperature, red being the coolest and blue being the hottest. And similarly, this is the spectra of the same object. And you can see different lines here, and actually for the first time we see structures like this for argon lines. It was not, the structures in the argon lines were not detected before. So this is actually really incredible. An X-ray telescope is resolving the argon lines for the first time. So from observations like this, we will get insights into the formation and distribution of elements in our universe, because we can see these lines so clearly now for the first time. So obviously there are also going to be many observations made in the next 1 or 2 years from XRISM, and we are going to be able to learn a lot of things about our hot and energetic universe. We are all eagerly waiting for those observations and to see those results, that the observations that were not possible before. So the next mission, like I had mentioned briefly before, is Athena. It is going to again trace out the hot and energetic universe. It's going to be able to solve the missing variant problem, which is actually a really important problem in astronomy. We know that the models that we have, it predicts these the amount of variance that it predicts. Variants are basically the light emitters, the particles that can emit this radiation. The models predict about twice amount of baryon than we can detect. So we have this missing variant problem we are trying to solve. We don't know the answer to this yet, but Athena is going to be able to answer such questions. And then Athena will be able to answer how the supermassive black holes form and grow with time. It will be able to determine the spin of black holes, which is also a very fundamental quantity that astronomers have been able to be trying to measure for years and decades now. And it's also going to detect extrasolar planets, and it can trace the birth and death of stars. So to conclude my talk, this is actually a comparison between the time length for optical astronomy and X-ray astronomy. We are still at the very early stages of X-ray astronomy. As you can see here, optical astronomy began in right around the 1600s, around for 400 years. But compared to that, X-ray astronomy had begun just only like 40-50 years. So X-ray astronomy is still at its infancy compared to other areas of astronomy. So there are many undiscovered wonders that we are waiting to discover, and that is because the hot and energetic parts of our universe can only be explored with X-ray telescopes, and if we want to have a comprehensive understanding of our universe, we need these X-ray observatories. So yeah, that was the end of my talk. Thank you for being here.
I have several questions, if you don't mind.
Yeah,
First of all,
sure,
thank you for being here with us tonight. Awesome talk. When I looked at the spectrum you showed of highly ionized iron atoms, how hot do you have to get iron to strip away like that many electrons?
So for producing highly ionized ions, you need about 10 to the power 7 to 10 to the power 8 Kelvin temperature. So like 10 to the power 7 to 10 to the power 8 Celsius, something like that.
So awfully hot. So my next question is, let's just pick on galaxy clusters. What is it about a galaxy cluster that causes those kinds of temperatures?
There are a lot of things. There is this accretion happening, which is like it's accreting the surrounding matters because it's a strong source of gravity in the core, and it's kind of pulling all these matters. And then there are, in some of the system, there can be like supermassive black holes that shoots out these outflowing materials into the galaxy clusters. Yeah, these are some of the main sources of heating up of the gas, and obviously we don't understand galaxy clusters 100% yet, so there may be some of the things that still needs to be discovered.
But it's the gas that actually heats up to those temperatures.
Yes.
Is there a window in time where galaxy clusters are X-ray active? I mean, are there nearby galaxy clusters, do they shine in the X-ray part of the spectrum, or is this something that happened long ago as these clusters were forming?
So if it's already a galaxy cluster, it will radiate in X-ray. So if there is a nearby galaxy clusters, it is going to emit in X-ray because galaxy clusters are typically really hot.
Can I ask one more question?
Yes.
So yesterday, China launched an X-ray satellite, and I read the article on Sky and Telescope's webpage, and it talked about a unique, maybe novel, I'm not sure if it's novel, but a unique optical system they called lobster eye aperture. Could you comment on how that differs from, for example, Chandra? Doesn't Chandra use nested mirrors to direct the X-rays? And how would this lobster eye aperture on this new Einstein probe kind of work or be different? Or what does it get you?
So I'm not super familiar with lobster aperture, but the way, so the optical telescope or the optical astronomy differs from X-ray astronomy is in optical astronomy you can shine this light through, a system like a prism, and it will split you into this rainbow of colors, and it's so that's what you can get the spectra from. But in X-ray astronomy, you need these X-ray mirror assembly, like I think I showed in one of the slides. So you need these mirror to focus the radiation in the gratings, and then these light rays are incident on these detector, and they create an interference pattern. So there are bands of dark and light and dark and light and dark and light, and that creates the X-ray spectrum.
But the actual optical component up here at the top, the mirror, isn't it? They take the photons, the X-ray photons, and they reflect them off, like they graze the optic surface, right?
Yeah, it's a grazing incident.
Yeah, and they sort of nest those mirrors all inside each other, right? Is that true?
Yeah, because there's such a small ring of reflecting material, you've got more room inside to put another one in there.
Yeah.
Gain some more efficiency.
Cool.
You also want to focus the light there.
Well, thank you.
Question. You mentioned one of the missions of the X-ray telescopes is to look into the mystery of missing baryon matter. Can you explain a little bit more about what that is about, baryon matter missing issue?
So there is such a thing, a proposed thing called warm-hot intergalactic medium, which we astronomers assume that if the missing baryons might be there, but if that medium is there, you expect to see some of the structures in the spectra, like some absorption, even some emission features, and that you can only see in X-ray. And we didn't have a telescope good enough that was able to detect those lines. If we detect those lines with X-ray telescopes, we will confirm that there are some warm-hot intergalactic medium there. And that will mean that the missing baryon is basically there.
Can you say a few words about what your thesis was on? Was it in this area?
My thesis was on high-resolution X-ray spectroscopy. So Hitomi had launched when I did my thesis, but XRISM is fairly recent, so I was building tools to interpret the data from, let me show you, see there. Yeah, I was building tools for interpreting the data for Hitomi. Although it was very short-lived, we knew that there is going to be a mission that will be launched in 2023. So I was making tools so that we can understand the data from XRISM when it's available.
I'll take another stab. There was yet another X-ray satellite just launched by India. And its specialty is to study polarization in X-ray sources. How would you apply that to understanding either some of the things that you've been discussing or other things? Well, what's the value of seeing the polarization in X-ray sources?
You can, if you study the polarization, you can understand some of the properties of galaxy clusters, but I'm not sure if they're going to be detecting the lines in such precision. Maybe different properties of galaxy clusters, but if they're trying to measure the temperature or velocity, I don't think they're going to be able to do that with the polarimeters. It's just how the light bends and rotates, that's what they're going to track. Different things, equally important, but different things. Yes.
Very basic question. This is from a visual person, so I don't know much about these other different wavelengths, but why is it that our atmosphere, regular light can't pass through your hand, but an X-ray can? Why? What is it about our atmosphere that's able to block, say, X-rays and not visible light?
So there are different wavelengths. So the atmospheric opacity is determined by a bunch of factors, like the way the light interacts with those atoms in the atmosphere depends on a bunch of quantities that is actually related to atomic physics. Like so there is something called oscillator strength, which decides if the light is absorbed by those atoms, whether or not that's going to be emitted and how long after it's going to be emitted. So it's you see those optical photons because once they are absorbed, they're emitted immediately. And for the X-ray photons, that doesn't happen because of those atomic physics factors, and once they are absorbed, they're just absorbed there.
There could be a big difference in source brightness too. Medical X-ray, they're really beaming and bombarding, where I assume these are much fainter, smaller signals that you're trying to read. So like if you put your hand in front of a spotlight, you could probably see through it.
You mentioned when you were talking about the Athena telescope, one of the things that you mentioned that it can do is observe exoplanets. Why do exoplanets emit X-rays? Why would any planet emit X-rays?
Oh, okay. So the way to detect exoplanets, usually this is a very common way we detect exoplanets, is if there is a radiating source behind the exoplanet, and there are some movements that the exoplanet moves around the source. There is typically, when we see the radiation, we sometimes can see a dip when the exoplanet is blocking the source. Like how long it takes to pass the light source, we can measure different things to see what is the size of the exoplanet, how far it is from the radiation source, and so on.
So it's basically transit observations with X-rays as the source?
Yes.
Thank you so much. It's a fascinating topic and an exciting period of development. Thank you.
That was a great presentation.
Good.
We usually have refreshments back. So with that, we'll close the meeting. Our next meeting will be February 8th at 8 p.m., same old time. So thank you all for coming, and enjoy the refreshments at the back.
That was